Everybody, welcome. Welcome at part 2 of 2 sessions where we talk about advanced cutting materials. Advanced cutting materials, in the first part we mainly talked about some generalities about this type of materials, what makes them different from the more traditional cutting materials of today. And we also talked about diamond. PCD materials are could perhaps be the most ideal cutting materials we know today. But on the other hand, there are some shortcomings, and diamond bringing in contact with materials in which there is iron at certain temperatures is perhaps not a good idea, not the best idea one can have. And that means that next to diamond, there are other materials we classify today as advanced cutting materials. And that's what we are going to talk about today. Together with me, again, are the people of this team. There is Alesia, Margarita, and Olivier. They take care of the technical stuff around the broadcasting. And I have 2 colleagues of mine, Francesca and Perola, who are product experts when it comes to advanced cutting materials. They will mainly help me later when questions comes in, because they know quite a lot about applications with advanced cutting materials, where to use, where not to use, and that type of stuff. There is quite a lot of extra material available around this subject, and I draw your attention already here. If you want to receive reference materials about advanced cutting materials or machining in general, just send me a message and I make sure that you have them in your mail. First, a few words on what people call hard turning technology, or in the meantime, it's extended even further. People more and more start talking about hard machining technology, meaning the technology is not used only for turning applications anymore, but also in other typical machining operations like milling and drilling and that type of stuff. Now, hard turning, where it started, is an important technology, became an important technology. And you have to see it less from a technological perspective, but it's more about that people in manufacturing constantly, they are looking for production processes that gives them smarter solutions, lower costs, higher quality, quicker setups, lower investments, smaller tooling inventory, and all that type of things. And machining of hard materials, which is traditionally the field for grinding applications, there we see that hard turning compared to grinding in a very big number of applications offers improvements in a sense of lower costs and higher quality and so on. So the question about why do we need hard turning is perhaps not so much a technological thing. It's more a techno-economical thing. It's more about the overall picture in manufacturing. And hard turning, what is hard turning then? Hard turning is turning in hard materials. Hard machining, the extension of it, is machining in harder materials. Now, the definition of what we call harder is changing over time. Because depending on what is available as cutting materials in the more classic things like carbides, where there is a very clear evolution still going on towards harder carbides or more versatile carbides and stuff like that. And that is influencing the answer to this question. On the other hand, also advanced cutting materials, the CBN materials and so on, they also still evolve quite a lot. And that means that, from where do we call something hard turning is over time changing. Traditionally, we said in the past, there were two kind of thresholds. One threshold was material hardness somewhere around 300 Brinell. And it was said that when your material hardness is below, and we were then mainly thinking in terms of steels and cast irons, to some extent stainless steels, but we said when the hardness is below more or less 300 Brinell, we call that traditional machining. I on purpose do not use the words machining in softer materials because, what is softer? But 300 Brinell was kind of a borderline. Below 300 Brinell, it was kind of, don't worry, things are going fine. You don't have exceptional problems during machining. So it's a relaxed situation. Above 300 Brinell hardness, and from where the 300 Brinell? Well, that came from empirical data, from doing and observing. Above 300 Brinell, we saw things were changing. We saw that cutting forces and how they develop, heat during machining, temperatures during machining, structural changes in workpiece materials. We slowly slipped into a different situation. But still rather handleable, okay, it works. A second border, and I remember when I was a young man, it was kind of a serious border then. That was 45 Rockwell C. Again, from where 45 Rockwell C? By observing, by experiencing. And 45 Rockwell C was kind of as a solid wall. We could not break through when doing machining, traditional machining, turning, milling, drilling. If a material hardness was above 45 Rockwell C, we had to go to grinding operations, honing operations, lapping operations, all that type of stuff. And that was kind of a dogma, I could nearly say. That was it. Machining we did in materials with hardnesses up to 45 Rockwell C. Beginning of the 80s, late 70s, beginning of the 80s, when we started slowly to see different types of cutting materials, we saw that we could go beyond that 45 Rockwell C. But still, it became possible, but we had to take special precautions. Rules were not as the rules we knew from the traditional machining. And that's when we start calling hard turning technology. So if we do turning in workpiece materials with hardnesses above 45 Rockwell C, the original definition, that's what we call hard turning. Today we go up to 70, 75 Rockwell C. And I know what you see on the screen now are other figures, but as I said, the figures here are ever changing. I think more that you have to focus on the process itself, and depending on the phenomena you see taking place when you do machining, you should recognize for yourself, am I in the traditional, let's say, soft machining, or am I more in the field of hard machining? The hardness here is a key figure. I mean, if you take traditional soft turning, and if the hardness is 200 Brinell or 250 Brinell or 280 Brinell, it plays a role, but minor. In the hard turning field, however, a hardness of 45 Rockwell C or 50 Rockwell C, be careful with that scale, that Rockwell C scale. It's not a linear scale. So the hardness figure, the number, is a very crucial information here. Hard turning, for the rest, is comparable with soft turning. I mean, we do it on lathes. We have tool holders. We have inserts. We talk about the traditional cutting conditions. It's if you master soft turning, hard turning is not so difficult to introduce in a workshop. If we look to cutting materials, what made it possible from the beginning, and I still think today is the traditional material for hard turning, is PCBN. PCBN, polycrystalline cubical boron nitride, within a couple of minutes, we are going to dive into that. What is it, and how do we use it, and where do we use it? It's with the becoming available of that material that hard turning became an option we could do in reality. Today we also can do it with cermets, with ceramics. The question there is more an economical question, I think, than a technical question. What would be best? But I dare to say that the most universal cutting material in hard machining technology is most probably PCBN today. Hard turning, as it is a turning operation, it's a single point operation. It's done with a tool with a well-defined cutting point, cutting edge. And that makes it so much easier to apply that grinding, because grinding is a machining operation with an undefined cutting edge. The cutting edges are somewhere on a grinding wheel, and there are a lot of them, but nobody knows exactly where they are and how they are positioned, what the geometry is, and so on. So hard turning, being single point machining, makes it possible to produce rather complex shapes and forms in one operation. To do it successful, hard turning, you need quality equipment. You need lathes which are, I would nearly dare to say designated for the process. The fixturing equipment is very important. If I look to lathes and fixturing equipment, it's the stability of the process, the stability of the equipment during machining, which is for me crucial. And of course, tooling, the cutting edge itself, needs to have the correct properties to be capable to machine in those harder materials. Hard turning is an operation. We do quite a lot of applications. You can do external turning, internal turning, grooving, threading, whatever you want. What we do in soft turning, we can do from an application perspective in hard turning. And if you look to the attractiveness of this, also when you compare it with grinding, is that it delivers good results. Given that you have the correct lathe, that you have been spending correct attention to fixturing of tools and cutting and workpieces, and that your tooling is in line with the demands which are on such a situation. Successful hard turning, so you need sustainable cutting edges. I use the word sustainable here in a sense of durable. The cutting edges have to keep over a longer period of time their initial properties, their initial geometry, their initial material structure, and so on, in even when used in heavy conditions. Because the working conditions of a cutting edge in hard turning applications are rather severe. We are going to come back to that later. Rigidity, as I already said, is critical. Rigidity of the lathe, of the fixturing, of the tool. Rigidity makes or breaks the operation. And very clearly, hard turning is technology driven. Hard turning is an operation. Let's not exaggerate it. Let's not make things too complicated. But I dare to say hard turning, hard machining needs to be done by people who know what they are doing. It's a very strong technology-driven process. So machining technology, process technology, material, work holding, every single element in the process deserves specific attention. A picture, the moment you make it, is wrong. The moment I show it, it's wrong. I mean, where are we drawing the lines? If we're talking about machining of harder workpiece materials, as I said, somewhere the 45 Rockwell C hardness was in the past kind of a limit. Today, what we see is that over 45 Rockwell C, we can use carbides, we can use PCBN materials. We can use grinding. Grinding is the alternative we are using since ever for this type of materials. Today, carbide PCBN also enter the arena. They also can do things here. The difference between carbide and PCBN in the area of below 55 Rockwell C, let me put it like that, is perhaps not a technical thing, that's more an economical thing. You know, with hardnesses up to 45 Rockwell C, with the carbide grades we have today, it's possible doing it. It's possible cutting. The question, of course, is how long will the cutting edge last? How sustainable is a carbide cutting edge when used in that type of material hardnesses? That's the big question. For sure, the sustainability of a PCBN cutting edge is longer, is better. That is for sure. But on the other hand, and I think most of you know that if you look to the purchasing cost of a PCBN cutting edge, it's a bit higher than carbide. And then comes the techno-economical question about how much money do I spend to gain which advantage? And you could say, yeah, okay, I spend more money on PCBN, but I gain the advantage of long tool life. But the application, on the other hand, think for work to be done in small batches, for instance, perhaps you don't need that. Perhaps a short tool life is acceptable for you. And then is the question, yeah, should you spend more money on a PCBN cutting edge while you could do the same job? Limited tool life is for you not a problem. That's my thinking here. If you can do it with carbide, which is from a purchase perspective cheaper. So that's what I mean. If you start to have this type of discussions, be careful, because next to the technological discussions, which one is better, which one gives you longer sustainability of cutting edges in this type of application, you have to confront that, you have to oppose that to the economical considerations. Longer tool life, yes, but do you need it? If yes, yeah, then the answer is obvious. If not, yeah, then there can be a discussion. In general, one could say that, especially in comparison with grinding, hard turning economics are making hard turning, milling, drilling, mainly with PCBN cutting materials, the best choice in hard workpiece materials. I'm not going to read every single sentence here on this slide, but nearly every aspect, every element in this process is in favor of hard machining compared over grinding, which makes hard turning the better alternative. It's one of those technologies that before we were talking about, I remember when I was younger, we were talking about things that were still not possible. I mean, when I was young, it was not possible to machine hard materials. It was not possible to do multi-edge turn. There were a number of impossibilities in those days. And one of those impossibilities, namely the hard machining, the machining of hard workpiece material, became possible with the dawn of PCBN cutting materials. PCBN as a material, it's synthetic, it's a compound material, and it's not so new. The first time cubic boron nitride was synthesized was already in 1842. Polycrystalline cubic boron nitride, which is a compound material. You have PCBN cubics, PCBN grains connected to each other with a binder material. As such, it became a material with which it's possible to machine, to cut other materials, was introduced somewhere in the 1970s by an American company, General Electric. So it's advanced in a sense of that the possibilities we have with it are very advanced. But saying that this is new is not exactly true. So a composite material with a metallic or ceramic binder, that's what we talk about. It's synthetic. It's man-made. You don't find it in nature. And as far as we know, as a family of materials, it's the second hardest material we know after diamond. And if you look to this PCBN materials, and be careful, I make the same remark as I made last time, PCBN, I remember beginning of the 80s, PCBN was one material. There was one PCBN material. Today it became a family of materials. And we talk about PCBN grades, like similar to carbide. We talk about coated PCBN and so on and so forth. It became a whole family, but there are two big branches in that family. It's low and high content CBN. Now, high content, low content CBN, it relates to the mixture of CBN grains and composite and binder material. Low CBN, low percentage CBN, is a family of materials that offers you higher toughnesses and lower thermal conductivity. Perhaps now you are not familiar that we talk about lower thermal conductivity, but I come back to that within a few slides, why that is important. High content CBN, on the other hand, is harder, higher wear resistance, and the thermal conductivity is also higher. That makes that the two families aim for completely different applications. Very important if we talk about CBN. Next to that, we are aware of that it's a material compared with the traditional carbides that offers higher hardnesses. The abrasion resistance is noticeable higher. It's chemical stable. It doesn't react chemical with iron, the disadvantage of diamond I mentioned a couple of minutes ago. That makes it so exceptional. However, full possibilities of the material, PCBN, can only be achieved if and when the cutting edge geometry is well defined, is well thought over, and is made appropriate to the application. Machining, we have been talking in previous sessions about machining and the different phenomena. One of the phenomena we have in machining is that heat is generated. That heat spreads out partly in the chip, partly in the tool, partly in the workpiece. That heat, normally we want to control, because if the heat is getting too much in a certain direction, the temperature there will go too high, and that leaves us with certain problems during machining. However, if we focus a bit on the heat going into a workpiece material, increasing the temperatures of the workpiece material, there is one property of workpiece material that is influenced by that high temperature, and that's the hardness. And that's what I try to show in the diagram here. If you have materials with hardnesses which are at room temperature rather high, if we heat them up so the temperature becomes around 7, 8, 900 degrees Celsius, the material softens. And machining, or this is perhaps the secret of hard turning, hard machining in general, if I can make that just before the material is being cut, is being machined, the temperature there is so high that the material softens to a level that makes it easier to cut, hard turning is not a big problem. It becomes soft turning at higher temperatures. And that is the whole secret. There are two problems, however, here. This temperature should be kept local. I cannot have that the whole workpiece rises up to 800 degrees Celsius, because then I have a problem. It should be very local. Just before the cutting edge, I need that high temperature. I need that softening effect. So the question is, how can I make that happen? And the second thing is, I need a cutting edge with properties that can function constantly in that type of environment. Temperatures of around 800 degrees Celsius, 900 degrees Celsius. And that's where PCBN outperforms carbide. Quite a lot. Reaching that heat, reaching that high temperatures, however, we have to make a distinction between roughing applications and finishing applications. Roughing is big depths of cuts and feeds. General definition of roughing. In such a case, that enough heat is generated to increase the temperatures to the wanted level is rather easy. However, if we talk about finishing, small depths of cut, small feeds, raising temperatures to the wanted level is not so easy, because the heat generated is much lower. Well, and here comes around the corner low percentage PCBN, because if we do this with a cutting tool with a low thermal conductivity, the whatever heat which is generated don't go into the tool but goes into the workpiece, and perhaps that little bit extra that goes into the workpiece is for us just enough what we need to raise the temperature there where we want to have it just before the material is being cut. And that's why it's so important to understand that we have two families of PCBN materials: low percentage CBN, high percentage CBN. Cutting edge geometries, with what we talk about mainly in case of PCBN materials, is the cutting edge. The cutting edge chamfer. This chamfering we need to strengthen the cutting edge. I always say the real quality of a CBN, PCBN insert is perhaps seen on the chamfer. That chamfering needs to be done with the appropriate care for quality, because that chamfering is what we need to handle the weak part of CBN, being the brittleness, the sensitivity PCBN has for shipping, for breaking. And if you look to chamfers on cutting edges in CBN inserts, trust me, you see differences. Some of the chamfers, it's very, very, clear that it's high quality grinding and honing. Other chamfers, they look, not so good. Let me put it like that. So if you want to know the quality of an insert in PCBN, my message is look at the edge chamfer. There you'll see quality. Also, the edge chamfer is one thing. There is also the honing between the rake face, clearance face, and the edge chamfer. You need to avoid sharp edges. So honing is another important part when we talk about geometries here. And it all goes to cutting forces. During machining, we have cutting forces. By the way, the next session here we are going to dive into very deeply in the aspect of cutting forces. But cutting forces exist during machining. Those cutting forces are going to put a mechanical load on a cutting edge. And if there is no balance between a cutting force and the strength of a cutting edge, you end up with a broken cutting edge. Very simple. Now, cutting forces in case of hard machining are relatively high due to the hardness of the material. So we have to cope with relatively high cutting forces. And one trick we use for that is the edge chamfer. With an edge chamfer with a certain width and under a certain angle and things, we can make sure that there is a better and an easier balance between the main cutting force and the strength, the stability of a cutting edge. And we can minimize the risk for shipping, for breaking. The same goes if we focus on the feed forces. Also there, two sharp cutting edges would make them prone for breakage, for shipping due to feed forces during machining. Also here, an edge chamfer will help us to create a more stable cutting edge. So PCBN as a cutting material without the appropriate cutting edge geometry to give the material the resistance against fracture, the resistance against shipping, we need that cutting edge chamfer. And that's why you see when people start talking about these materials, they spend, I think, at least as much attention to the actual cutting material as to the cutting edge geometry. It's a very important element in the picture. Where do we use these materials? Again, I blacken out like I did in the previous session. if you want copies of this, of course, you will see the full text. I hide the text here, not because it's a secret, but just to make sure in the limited amount of time we have available that we focus on the important things. Typical for CBN materials, PCBN materials is hard workpiece materials where the hot hardness is the important element. We can use PCBN also in soft and abrasive materials. There the hardness and the abrasion resistance of PCBN is going to be the features that are important for us. And there are applications in the so-called difficult to machine materials where also hardness and abrasion resistance is important. As far as I'm concerned, PCBN is the standard cutting material for hard machining technology. Standard in the sense of broadest applicable, most versatile in this type of applications. If we want to have a discussion about ceramics and ceramics, also possible, but then it's more a techno-economical discussion we will have to have. PCBN is ideal for dry machining, and there are even applications where it's an obligation that we use PCBN in dry machining. Again, remember, one of the secrets for hard turning is that I want to raise the temperature of the material just before it's being cut, high enough to soften the workpiece material, enough to make it possible to machine it. So that I don't need cooling is a possibility, is an advantage. There are applications where I should say it's forbidden to use cooling. Obviously, very typical, I'm thinking on automotive applications and so on. PCBN is the ideal material for automated production, automated machining. Because the cutting edges show a rather high sustainability. Again, sustainability, my definition here is, for a longer period, they keep their initial cutting possibilities, geometry, structure of the material, and the wearing out process develops rather constantly. So we must not stop the production too often to replace cutting edges, and we know when to stop it. It's a rather sustainable situation. Hot hardness, the hardness it has, and the ability to keep that hardness at higher temperatures makes PCBN specific, and abrasion resistance, the hardness in general. It's the material that challenges grinding in nearly every application. It's a rather good material, but you can't use it everywhere. Like always, everything has its limits. Also here, PCBN, there are applications where I would say, or for technical reasons, or for economical reasons, PCBN should not be your first choice. It could be an alternative, but I think there are better alternatives in case of soft machining, stainless steels, unhardened materials. There are a number of situations where I should say don't use PCBN. There are a number of applications where it's possible, but we need to take certain precautions to make it possible. Cooling is possible, but you should question it. Do I really need it? And there are a number of situations. Think on I need my heat, I need my temperature to soften my workpiece material. There are a number of applications, I think mainly in interrupted cutting and so on, milling applications, machining of splines on a lathe and so on, where I would say do not use cooling. No cooling should be your basic choice. Ship breaking when using this type of materials is normally not a big thing, because most of the materials we machine fall under the umbrella of harder materials, giving normally shorter ships anyway. with some softer materials. Ships can be long and stringy, and here and there, even with PCBN, we use ship breakers, but it's not so often. PCBN, for me personally, I like it, the material, and I like the application hard machining when it comes to tool wear, tool deterioration, because tool deterioration in a lot of cases with these materials develops as described in the books, I could say. It's tool deterioration analysis, tool deterioration correction is I think very, very, very. I don't want to use the word simple because tool deterioration is never simple, but rather straightforward. What you see is what you get, and the recipes, if to take out what you see if you don't like it, are rather straightforward. If you see this and you don't like it, do that. End of story. Be careful if we talk about tool deterioration, especially when you make the jump to tool life afterwards. Breakage is a rather common thing in PCBN. Normally we say with carbide, less than 10% of the cutting edges should be broken in general turning conditions. That 10% is based on observations again. With PCBN, there is a tendency that you will see more broken cutting edges. It's typical for the application, harder workpiece materials, stuff like that. However, if you notice more broken cutting edges, at the same time you should evaluate rather seriously if the initial wear you have on a cutting edge, if you didn't let it become too big. Because here, too big tool wear will lead very fast to breakage. Remember what I was telling you about the cutting forces and the chamfers and so on. Wear will weaken your cutting edge, and a weakened cutting edge will break faster. That's what you have to remember here. But if you keep that under control, and if you have the normal wear patterns you should see, what you see is that application, tool deterioration, tool life, and through tool life, the bridge to machining economy is a rather very stable situation. Ceramics, the third family of advanced cutting materials. We talked about diamonds, we talked about PCBN. Today we also have ceramics. Ceramics, also here, it's not exactly new materials. Ceramics we use, it's inorganic materials, it's non-metallic materials. We use them since a long time in all types of applications. We also use them in machining for cutting. And the properties which we are interested there are the hardness, high hot hardness, keeping the hardness at higher temperatures, the high strength, but the strength comes with acceptable toughness, very good chemical stability, both in low and high temperatures, and a rather good resistance against thermal shock. That are the properties of technical ceramics that makes them attractive as cutting materials. So remember, high resistance to heat, hard, high resistance to wear, but lower toughness. That are the three key things you have to bear in mind. Also here again, like with all the other materials, ceramics became over time a whole family of materials. Today, basically, we make a distinction between the so-called white ceramics or the black ceramics. I'm going to describe them briefly. And next to those two main groups, there are also the Sialon materials, silicium nitride materials, and the whisker-reinforced ceramics. That's a bit the five big families. If you compare them with carbide, what you see is that, and you have to see it at more elevated temperatures, the hardness of these materials is above the hardness we find in traditional carbides. But again, with graphs like this, development is not standing still. The properties of carbides are changing, and properties of ceramics are changing. It's more an indication. You have to see diagrams like this. It's an indication of what it is. Where do we use ceramics? But we use them from a material perspective. I would say roughly in all materials: cast irons, superalloys, hardened steel, steels. Perhaps some exception for stainless steels, but even so, it's possible. But the selection process is important, and not every ceramic will fit for every workpiece material. You have to make sure that you make the correct selection. High hardness with low strength, high brittleness, toughness and thermal conductivity. That is the things you have to think on when you talk about the white ceramics. For your information, historical white ceramics were the first ones we used when we did machining with ceramics. And still, for a lot of people, and perhaps I should look at myself first, for me, ceramics is still that, it's good, but it's brittle, it breaks fast, and so on. One of the misconceptions, perhaps, that limits the usage today still a bit. Because you have also the mixed ceramics, black ceramics, which is ceramic materials, compound materials. It's ceramic grains, one could say, with the binder material. The big advantage of black ceramics compared to white ceramics is that they can handle more extreme cutting conditions. The toughness is better. They are not so sensitive for breakage. Mixed ceramics, black ceramics, can be a serious competitor for PCBN in hard machining. But that's an evaluation you need to make not only based on technical considerations, but also on economical considerations. Silicon nitrides, higher resistance, better ability to handle thermal shock, higher fracture toughness. Silicon nitrides kind of were the gate where we started to use ceramics also in milling applications. In the meantime, we use also other types of ceramics in milling. An important thing to know here is that the low thermal expansion of these materials makes them very resistant against thermal shock. That's why I think it's dangerous to say, but silicon nitrides are perhaps the basic, or should be the basic choice for milling with ceramics. But as I say, be careful with that type of thing. You have the sialons, which is a mixture of silicon nitride and the traditional aluminium oxide material. The name sialon stands for silicium, aluminium, oxygen, and nitrogen. It's a lower cost alternative than whisker reinforced materials. And that brings me to whisker reinforced materials. That's kind of materials like you have concrete and you have armored concrete. Armored concrete, you put iron bars in to make the concrete stronger in a sense of more resistance against breaking and stuff like that. Well, whisker reinforced materials is kind of the same thing. In the ceramic matrix, whiskers, kind of threads, are built in, and those threads create strength in the structure, create resistance against fracture. These materials are rather flexible when it comes in the ceramic domain. You can use them in quite a lot of applications. How do we use ceramics? High cutting speeds with balanced feeds is the thing to worry about. In general, think in terms of bigger depths of cut, which some of the older people here in the audience will perhaps say, bigger depth of cut. We talk about ceramics, aren't we? Yeah, we talk about ceramics, but still think in terms of bigger depths of cut. If you have interrupted cut, make sure your cutting temperature is high enough. That's for the softening of the workpiece material again. Ceramics, like with PCBN, when we start talking about tool deterioration, is a very nice material to work with. Tool deterioration will nearly develop like described in school books, in textbooks. It's very beautiful. And solving it, if what you observe is considered a problem, is very straightforward again. If you see this and you don't like it, well, you have a list of remedies you can apply to handle the wear problem. Here, a different way of showing. I like this as it is so simple to illustrate visual. The blue domain indicates trouble-free machining with ceramics. Around the blue domain, you have all the things that could make your life miserable if you look for that trouble-free machining. Vertical, you have the cutting speed. Horizontal, you have the feed rate. And you just have to read in the diagram. If you observe something, for instance, if you observe vibrations, which is there to the left, and you don't want vibrations, well, you increase the feed. Simple. Cooling is always recommended. HPDC cooling is best. That has a lot to do with the ship breaking. HPDC is the high pressurized directed cooler, what we call in SECO jet stream cooling. Ceramics are still limited used. I think the ceramics today are underestimated. But as I say, it's to some extent there is some lack of toughness. Not every machine tool of today can handle ceramics, is giving us the stability, the power we need. The ranges are still rather limited, especially if you compare with carbides or with PCBN materials. And the next one is perhaps the most important one. And as I say, I'm the first one to admit this for myself also. It's lack of knowledge and expertise of the machining engineers, operators, with the ceramics of today. You know, years ago we were confronted with ceramics. We build our own experiences with it, and we live by those experiences, ignoring a bit that also in ceramics development is going on every day. On the other hand, a number of possibilities we have with ceramics today, which were unique in the past, in the meantime, can be challenged by the available carbide materials. Summary: advanced cutting materials made a number of things which were in the past not possible. I think that's been their biggest contribution to machining. In the past, machining hard materials, super precision machining, dry machining, was all applications labeled impossible. Today, with or PCD, the diamonds, or with PCBN, or with ceramics, a big number of these impossibilities became possible. Not only technical, but also economical, justifiable. PCBN, as far as I see, the material, the cutting material for hard machining, dry machining. Diamond, what we talked during session 1. As far as I'm concerned, perhaps I'm exaggerating a bit, but for me, this is the basic material for every workpiece material in which there is no iron, because diamonds today still is struggling with that iron thing, you know, iron, higher temperatures, PCD, there are issues. But if those are not there, I mean, the iron combined with a higher temperature, to be honest, in my eyes, nothing beats PCD. Huh? So aluminium machining, aluminium turning, milling, whatever, it's PCD. Ceramics, a little bit should I say the black sheep in the family, or am I exaggerating now? I don't know, but ceramics it's a big branch in the meantime, in the family of advanced cutting materials. Remember, you have big groups there: the white ceramics, the black ceramics, the whisker reinforced ceramics, the sialons, the silicium nitride ceramics. If you look to the total picture, yeah, they serve a big domain of applications, ceramics. Selecting the most correct material, if you have to do it manual, I don't envy you. Because for 80% they are all overlapping each other, and as I said, from a purely technical perspective, it could be a cumbersome exercise to find out which one is best. I would say trust more there on modern technology. We have all the software available to select tools, to select the best possible tools, not only from a technical perspective, but also from an economical perspective. Trust on that to find out what could be in your application the best selection of cutting material. And most of all, perhaps, make sure you possess yourself enough knowledge to fully, when you observe an operation, to fully understand what you see. And if what you see you don't like, to know what to do. Again, as I said, there is a whole bundle of information available for you related around advanced cutting materials. Also, more information general on modern machining technology. You are just one email away for being able to put your hands on all that information. And that brings me roughly to the end of this. Over the two sessions together, what I try to sketch you is a picture of, we have traditional machining, we have hard machining, and that relates to the workpiece materials. Traditional below 300 Brinell as a guideline. Hard machining above, should I still say 45 Rockwell C? I don't know. In between, you have the in-between zone. In those three big domains of applications, if we focus on cutting tools, there are quite a lot of features we can talk about. The most important one is perhaps cutting materials. For traditional machining, into hard machining, carbides today are the most versatile cutting material, broad applicable. Next to carbide as the versatile cutting material, you have the more advanced cutting materials, the diamonds, the PCBNs, and the ceramics. In a number of applications from a technical perspective, these advanced cutting materials are superior to carbides. However, in a number of applications, you have to look beyond technology and also consider economical considerations if you have to make a selection. That, in a nutshell, is the picture I tried to sketch you. But now let's see about questions. Quite a lot of questions. I hope my colleagues are ready to support me in the questions. Let's see the time we have left. Paola is there, I see. Perfect. I have a question here. Is a CBN insert more convenient in hard material than a carbide insert? But I think that's a question, yeah, I already answered. You have the technical perspective, but next to the technical perspective, you have also the economic perspective. Which one is most convenient depends on the exact hardness of the material, but also, for me at least, it depends on the batch size of the job you have to do. Do you need to produce one workpiece or do you need to produce 10,000 workpieces? Is also something you need to take into consideration. I don't know if my colleagues have something to add to it. Perola?
Absolutely, I do agree with you. It's up to the batch sizes, and also in some cases the quality of the workpiece that you are producing, and also I will say the hardness of the material is also a critical point. If you come over like 60, 61, 62 accuracy, then the carbide in general have quite big problem, I will say.
Yeah.
So that's,
Thank you. Thank you for adding that. Fully agree with what you say. There seems I have a second interesting question from André. I recently did research on hard turning steels using experimental ceramic tools. Aluminium oxide mixed, I suppose, with manganese oxide and aluminium oxide with chromium. I have to admit that's beyond my present knowledge. I don't know, Francesco Perola, you met these things already?
I haven't.
Me too.
No.
So
maybe you can share the research.
I was just going to say, André, sorry, but you have us here. We look like little boys now. If you have information you can share, we would appreciate that a lot. The next question we have still time. The next question is from Osni. What's the ideal depth of cut in relation to the size of the edge preparation? Depth of cut, with other words, versus the chamfer size. Francesc, I think that's a question you can give some comment on.
Yeah, I believe that the recommendation is to not go above the length of the chamfer. That normally is the depth of cut used in CBN. What do you think, Perola? You are a specialist.
Yes, I will say, around 0.1. Our egg preparation is standard between 0.1 and 0.15 in the width. So around there, I would say.
Yeah.
It's no advantage to have a large depth of cut, especially for finishing hard turning, because it creates quite a lot of problems. You generate more cutting forces, you generate more heat, and that actually means also that if you have a larger depth of cut in finishing hard turning, that means also that you need to reduce your cutting speed to compensate for the heat in the shear zone. So try to keep a stable depth of cut, no big variations, and around 0.1, I will say.
But it's important to a point that Patrick said about high content CBN, low content CBN, when we talk about hardened steel, or when we talk about soft material, abrasive, then here we can make that depth of cut of 1 millimeter. Cast iron, for example.
Good. Thank you very much for elaborating a bit on this. We have some more time. A question here. I also hear about hexagon boron nitride next to cubic boron nitride. What's the difference? But it's about the structure. It's about the crystalline structure. Hexagon boron nitride. No, let me say like this. Everybody knows the difference between, or everybody, I suppose a lot of people can appreciate the difference between graphite and diamond. It's both carbon, but the difference is in the structure. Well, hexagon boron nitride or cubic boron nitride, it's exactly the same. It's boron nitride, but the crystalline structure is different. A hexagon structure makes it soft. I don't know, some of you know perhaps that boron nitride is also used in cosmetic products, huh? But the hexagon form then. Cubic boron nitride is the material we use for machining. It's much harder, it's extreme hard. So it's the same material, hexagon boron nitride and cubic boron nitride. It's the same material, but the crystalline structure is different. For your information, the first session I said we are not going to talk about Wurtzite CBN. Well, Wurtzite CBN is also boron nitride. Oh, sorry, I shouldn't say Wurtzite CBN, but Wurtzite BN. It's also boron nitride, but again, the structure is different. The crystalline structure is different. Okay, one last question. Is MQL cooling, the minimum quantification, minimum quantity lubrication cooling, a good option when using CBN, I suppose, in hard machining? I think that's a question I leave again in the hands of PO or Perola or Francesc.
Francesc?
Yeah, MQL is a coolant technology that sometimes is used, sometimes not. I've never seen too much in the automotive plants use CBN with MQL. I have seen more when it's soft machining. But of course, if there are the need for some specification, could be. But my experience, I've never seen MQL in CBN. It's normally dry machining. Totally
Yes,
dry.
and I will say that is actually one of the really big benefits with PCBN, that it's possible to do it dry, because if you look on the I would say the cost. I would say the cost for example, the coolant, it's in many cases can actually be higher than the cutting tools. So that's environmentally friendly also. So it's many benefits running dry.
Perola, you touched something very important there, because cooling is rather expensive compared to, for instance, tooling costs, and you don't need cooling when you use CBN. So why should you use MQL, which is even more expensive in some way than traditional cooling, when you don't need it anyway?
Yes.
It's a bit, I don't know the technical part of it. Could be reasons to use it, but if I concentrate on the economical side of it, I don't see any I agree there with my two colleagues. I don't see any reason to apply it. But time is up. Once again, thank you all for listening to this. Thank you to my colleagues for being here together with me, for helping out. For all of you, as I said before, if you want to have more information, just let us know. Whatever we can help you with most pleasure, of course. Next session is end of November. And the next session, today we mentioned slightly some things about cutting forces and so on, but next session I want to dive in seriously in that thing, because as the title says, precision and productivity is what people are after in machining, but precision and productivity is only possible if you make that you are fully in control of a machining process, also from a mechanical perspective. The cutting force and everything that comes together with cutting forces. But that's for next time. Hopefully, I see you there again. In the meantime, again, on behalf of my colleagues and myself, thank you. We hope you had an interesting session together with us.
Thank you.
Bye.